Good morning. In the previous class, we discussed butterfly computation. Okay. Here we have taken the inputs as complex numbers. Okay, it consists of real values and imaginary values, and total factor is also complex values, and output is also in the form of complex values. Okay. Finally, here we get the AR dash, means the real value of the output. Okay, that is AR plus BR R minus BIWIR. Okay, similarly we calculated AI dash, BR dash, okay, and BI dash. Here we consider temp1. Temp1 is equal temporary value 1 is equal to BRWR minus BIWIR, and temp2 BIWRR plus BRWIR. Okay, just remember these equations. Okay, AR dash, first output real value AR plus temp1. BR dash, second output real value BR minus temp1. Okay, what about the imaginary value of the first output? AR dash is equal to AI plus temp2. Okay, BR dash, the second output imaginary value is BI dash equal to AI minus temp2. Temporary value 2. Yeah, temp1 and temp2, these are the variables. Just remember what is the temp1? BRWRR, BIWIR. Imaginary value of the second input and the real value of the second input, real value of the total factor. Okay, imaginary value of the second input, imaginary value of the second input, imaginary value of the total factor. Okay, what is the sign here? Minus sign. And here in this here the real value of the total factor and the imaginary value of the total factor keep as it is, and just interchange these values, these variables BR and BI, BIWR plus BRWIR. Okay, like that you can remember these equations: AR dash, AI dash, BI dash, and AI dash. Okay, please remember this equation, then you will get it. Okay. And also we discussed about n equal to 2 raised to m point FFT computation. Okay, there are two types of FFT algorithms here. One is decimation in time and decimation in frequency. Okay, what is decimation in time? Inputs are in bit reverse order. Inputs are in bit reverse order. Outputs in sequence. See here, the naturally occurring input time samples indices are bit reverse and processed by the above algorithm. The frequency domain output is in the natural order. Such a computation is called as DIT FFT algorithm, decimation in time fast Fourier transform algorithm. Okay, what about the DIF FFT, decimation in frequency fast Fourier transform? Here the time domain samples, that means inputs are in sequence, outputs, that means frequency values, those are in the bit reverse order. Okay, then zero padding. What is the use of zero padding? Here, what is zero padding? What is meant with the padding? For the given sequence, we can append some zeros. We can add some zeros. Okay, see here, if the sequence to be transformed is appended with zeros before computing the DFT. For the input sequence, we can append some zeros. Another objective of zero padding is to increase the transformed points to decrease the frequency interval between adjacent points represented represented by the x of k sequences. It can decrease the frequency interval between the adjacent points represented by x of k sequences. This leads to improvement in frequency resolution for representing signals in the frequency domain. Okay, just remember what is the use of why you go for the zero padding. Why we go for the zero padding. Okay, please go through this. Okay, next one is overflow and scaling. Okay, what do you mean by the overflow? We consider any, for example, you can consider accumulator, which holds only the 32 bits. Means if it exceeds 33, if it exceeds 32, what will happen? There occurs overflow. Okay, that's what, to avoid the overflow, we can do the scaling. We can do the scaling. We already discussed how we can do the scaling. Anybody? How we can do the scaling in TMS320C54XS processor? Using barrel shifters, right? We can normalize the inputs at the input side. At the output side, we denormalize it. Okay. For MAC, multiply accumulator unit. For the input side, we use the shifters. At the output side also, we use the shifters. Why? Normalize means you can change it some form. Okay, later we'll discuss about that. See here, the data must be properly scaled down before or during a butterfly computation to avoid overflow at any stage of calculation. Okay, to avoid the overflow, what we can do? We can do the scaled down before or during a butterfly computation. Overflow leads to a useless transformed result. However, excessive scaling leads to precision problems due to dropping of the least significant bits. Okay, thus one needs to have an idea about the magnitudes of the signal values so that scaling is applied only when needed. Scaling is applied only when needed. You can consider the equation A dash equal to AI plus BI WRR plus BR WIR. So it is temp to write temporary to value. Okay, temp 2 AI plus temp 2. Here you can assume WRR equal to cos theta. Here you can assume WRR equal to cos theta, WIR equal to sin theta. Okay, where theta equal to 2 pi n into k divided by n. Okay, WRR equal to cos theta, WIR is sin theta. Okay, theta equal to 2 pi n into k divided by n. In the factor, e raised to any value. Okay, that is 2 raised to pi n into k divided by n. Okay, substituting this WRR cos theta, WIR sin theta, and theta equal to 2 pi n into k divided by n. In the above equation A, now we will get, substitute here, A dash equal to AI plus BI cos theta plus BR sin theta. Here we will get the maximum value when we differentiate AI dash with respect to theta, equate to 0. Okay, dou of AI dash equal divided by dou of theta equal to, that means differentiation of AI dash with respect to theta equal to 0. Okay, then the maximum value will occur. Okay, here the AI, this is the constant value, then its differentiation is 0. Then BI, the differentiation of cos theta with respect to theta is minus sin theta, minus of bi sin theta, plus br as it is sin theta is a differentiation of sin theta with respect to theta is cos theta, that is equal to 0, minus bi sin theta plus br cos theta equal to 0. Okay, now we can send minus bi sin theta right side, then it becomes sin theta divided by cos theta is tan theta, then it becomes br divided by bi, br divided by bi. Consider right angle, triangle. Okay, this is theta here. Leave it. This one is theta. Yeah. Just remember this one is theta. Okay. What is tan theta here? This is hypotenuse. That I will write H. Hypotenuse, and this one is adjacent, and this one is opposite, right? Okay. What is the tan theta? Tan theta is opposite. Which one is opposite? Here, this one is opposite. What is this? This one is BR. Okay, this one is BI. Okay, BI, BR. Okay, then here tan theta is equal to opposite divided by adjacent, right? Adjacent, opposite divided by adjacent. What about the sin theta? Anybody? What is sin theta? Opposite divided by hypotenuse, right? What is the hypotenuse here? This one. This hypotenuse, square root of br square plus bi square. Is it? It's hypotenuse, right? In the right angle triangle. Hello? 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 What is sin theta? Anybody? Madhavi, what is sin theta?
Opposite divided by hypotenuse.
Yeah, okay. See here, this is theta. Okay. This is BR. This one is BI, right? This one is square root of, sorry, I'll write it here. BR square plus PI. Yeah, just remember it. Okay, this one is opposite. This one is BI. BI is adjacent, and hypotenuse is square root of BR square plus PI square. Here we know that tan theta is equal to, what is tan theta? BR divided by BI. That means opposite divided by adjacent. Adjacent is BI and opposite is BR. And sin theta. Sin theta is equal to BR divided by, that means opposite divided by hypotenuse. What is the hypotenuse here? Square root of BR square plus BI square. And what is cos theta? Adjacent divided by hypotenuse. That means BI divided by square root of BR square plus BI square. Okay, now We can substitute sin theta and cos theta in equation number B. In this equation, we can substitute AI as it is and BI cos theta plus BR sin theta. Okay, now it becomes, after substituting those equations, sin theta and cos theta, just remember what is sin theta and cos theta. Sin theta equal to BR divided by square root of BR square plus BI square, and cos theta is equal to BI divided by square root of BR square plus BI square. Now we'll get AI dash maximum equal to AI plus square root of BR square plus BI square. Please do the simplification, then you will get it. AI dash maximum is equal to AI plus square root of BR square plus BI square. Okay, how we calculate it? Consider any equation you can consider it. Any equation you can consider it. Here, out of how many equations here? Total 4 equations. AR square, BR square, okay, AI dash and BI dash, sorry, AI dash and BR dash, AI dash and BI dash. Here, in this textbook, we taken AI dash. Okay, consider that AI dash equation. Okay, now substitute WR and WI, cos theta and sin theta, and theta value, 2 pi n into k divided by n. Substitute in this equation. Okay, substitute those values, and here we'll get the maximum value when we differentiate this AI dash with respect to theta, that is equal to 0. Then the maximum value will occur. Okay, after differentiation we'll get like this. Okay, tan theta, and derive the sin theta and cos theta values, and after that substitute those values in the above equation, equation number B. Okay, then we'll get the maximum value. Okay, that is equal to AI plus square root of BR square plus BI square. Here, if we assume that the maximum value of each variable in equation number E, in this equation, okay, is 1. If all the values are 1, AI value is 1, BR dash value is 1, and BI dash is 1, then the maximum possible value that AI dash can attain is given as the maximum value of the AI dash when the each variable AI, BR and BI equal to 1. This is 1 and 1 square plus 1 square. Okay, 1 plus 1, right? It's 2. 1 plus square root of 2. 1 plus square root of 2. That becomes 2.141. The maximum value of first output imaginary is 2.141. Similarly, it can be shown that the maxima for other computed variables. What are those other computed variables? AI dash, okay, BR dash and BI dash in the butterfly computation are also equal to 2.414. See here, we consider this equation. For example, I consider this equation. For example, AR minus BR WRR plus BI WIR. Okay, find the maximum value for AR dash. How we can find it? Sorry, BR dash. Find the maximum value for BR dash. AR as it is minus BR WRR substituted as cos theta plus BI WIR as sin theta. Can substitute WRR as cos theta, WIR as sin theta. Now differentiate with respect to theta and equate to 0. Then the maximum value of the BI dash will get. Okay, when we after differentiation equate to 0, okay, then the tan theta will get. Okay, after that draw the right angle triangle. Okay, derive the equation for sin theta and cos theta. Substitute in this equation. Substitute in this equation, then we will get the maximum value of the BR dash. Similarly for AR dash, AR as it is plus BR, this one is cos theta. Okay, minus BIWIR. BIWIR. WIR as sin theta. Again, differentiation with respect to theta and equal to 0. Here, when we equate to 0, we'll get the tan theta. We'll get tan theta. Okay, then find out sin theta and cos theta and substitute in this equation. We'll get the maximum value for AR dash. Similarly for BI dash also. See here, the maximum value for all the variables AI dash, AR dash, BI dash. Okay, for all these variables, the maximum value is equal to 2.414 only. Okay, therefore, to avoid overflow, each input variable can be multiplied by 1 divided by 2.414. Okay, sorry, this value is 2.141. 2.414. It's not. Okay, 2.414. Now we divide the each input variable by 1 divided by 2.414. That is equal to 0.414. It means yeah, we can multiply each input variable by 0.414 or 1 divided by 2.414 to avoid the overflow. Okay. Therefore, to avoid overflow, each input variable can be multiplied by 1 divided by 2.414. That is equal to 0.414 before computing the butterfly. Okay, before computing the butterfly, we multiply each input variable by 0.414. Okay, the butterfly computation is modified by including this scale factor. Okay, in the butterfly structure, we include the scaling factor value AR plus JAI. Okay, 1 divided by square root of 1 plus square root of 2. That means what is the value of that one? That is 0.414. 0.414. Okay. Similarly, second input also multiplied by 0.414 to avoid the overflow. First, here you can find the maximum value of each input variable. Then derive 1 divided by 2 that maximum value. Okay. Then in the butterfly computation, each input variable is multiplied by 1 divided by maximum value. That means 1 plus square root of 2. That means 0.414. Each input variable is multiplied by 0.414 to avoid the overflow. Okay, in butterfly computation, we can show like this. Okay, now if a shift operation, okay, we already know that shift operations. We use those shifters to avoid the overflow also, right? If a shift operation which is simple to implement is used to scale the variables, the scale factor to avoid overflow should be 0.25. Okay, if a shift operation shifters we use, each input variable is multiplied by 0.25 or scaled by 0.25. See here in butterfly computation, AR plus JAI dash. So this one is BI. Okay, AR plus JBI. Sorry. Correct only. Okay, this one is AR plus JAI, BR plus JBI. These input variables are multiplied by 1 divided by 4. 0.25 means it's 1 divided by 4 only. Okay, here the second input also multiplied by 1 divided by 4. This one is 0.25 is the scaling factor for shift operation. When we use the shift operation, shifters, to avoid the overflow in butterfly computation, the scaling factor value is 0.25. What is 0.25? It's equal to 1 divided by 4. Okay, just remember here. Now, this figure, this one is butterfly structure that will be used in the DIT FFT implementation. This representation includes the scale factor as well as the total factor. Okay, so different ways to represent the butterfly computation. Here, for the input line, each input line, okay, we given the scaling factor value. But here, within the block, okay, we represent the scaling value 1 divided by 4 like this. Okay, please go through this. This is very important. These structures, butterfly computation structures. Okay, using any equations, okay, you can find the maximum value for all the values. That means AR dash, AI dash, BR dash, and BI dash. Okay, for all these equations, okay, the maximum value is 2.414 only. That's why each input variables can be divided by 1 divided by 2.414 or multiplied by 0.414. Okay, this is about the overflow and scaling. It's very important. Please go through this. Okay, in the previous year question paper, they asked this question. This is a very important. Okay, by taking some other equations, please practice these equations. Okay, please go through this. Okay. Now, bit reverse index generation. We already know that how we generate the bit reverse index, right? Here in the table, naturally occurring input variables and bit reverse index. See here 0 0 0. Write it in reverse order. Right to left. 0 0 0 0 0 0 0 0 1 as 1 0 0 0 1 0 0 1 0 0 1 1 1 1 0 1 0 0 0 0 1 1 0 1 1 0 1 1 1 0 0 1 1. See here, these are the bit reverse index. 0 0 means, see here, 4 2 1, right? 0, this one is 0 1 0 0. Which one is 1 here? 4. This becomes 4 2. Okay, 4 2. It's 6 1. Okay, 1 0 1 4 1 5 and 0 1 1 2 1 and 3. All ones means it becomes 7. Like this also you can find the bit reverse value. Otherwise, how you can find it? How you can find the bit reverse value? In the second module we already discussed. See here, initial index is always 0, right? Initial index is always 0 only, right? 0 0 0. Okay, here n equal to 8, right? What is the half of this one? N equal to 8. It's 4. For this initial index, you can add the half of the n value. Okay, 4 to 1 means 1 0 0. You can add it 1 0 0. Okay, here 0 plus 1. Here you can do, here the carry will move from left to right in this way. First 0 plus 1 1, 0 plus 0 0, 0 plus 0 0. What is the value? 1 0 0. For this 100, again we can add 10, half of the n value. 1 plus 1, 0, carry 1, carry and 0, 0, 1, 0. See. Then again you can add it, half of the n value. 1, 1, 0, like this. See, 1, 1, 0. Like this you can find out the bit reverse value. Otherwise you can write these values in the reverse order. Okay, then also we'll get the values. You see here, we calculate it like this. How we can find out the bit reverse value. Okay.